It's ideally meant to be a semester-long course, and you have that much material available from the note. But I'll try my best to actually condense and give you all the viewpoints on what reduction to characteristic P is all about. I'll be following the excellent resource of Hopch and Huneke, the tight closure in Equal Characteristic 0, Chapter 2. And it's available in this website. You can check out this website. It's there on Professor Hopch's website. There's a tilde here, but I'm pretty sure you guys have already figured it out. So you can go to this website, and as far as I know, it has not been published yet. It's an amazing piece of reference with Hopch and Huneke have written down. Their main objective in that expository note is to define what type closure in equal characteristic 0, but they dedicate one whole chapter, chapter 2, to reduction to characteristic P. And that's what we are going to be following today. And I'll be treating mostly the affine case of reduction to characteristic P and not the general case. So in fact, the reduction to characteristic P methods are known for any Noetherian ring containing a field, but I'll be restricting myself to the affine case because it's a lot more accessible and gives a nice idea of what reduction to characteristic P actually does. And the third one, even if you take up the general case, you still have to reduce to the affine case to solve the problem. So essentially, the affine case is a very important one and still pretty easy to see what's actually happening. Okay, as for the proofs, again, as I said before, the proofs are providing a lot of proof, but providing a little bit idea of the proof of what's actually happening there rather than complete proof. But if you're really interested, like if there's a certain theorem which I've typed down and you feel that you really need to know the proof, I strongly recommend that you go through these notes. Modulo a couple of typos. This is one of the best resources you can have for reduction to characteristic P. And why do we actually do reduction to characteristic P is because once you start with a problem on a ring of characteristic 0, then there will be a natural question on whether the same is true for a ring of characteristic P. And oftentimes you can prove something in characteristic P, and then using these reduction techniques, you can also try proving the same for rings of equal characteristic 0. Okay, so that's as far as what I want to say about the introduction. Last but not the least, I find that Professor Huneke is also part of the audience. So if you have any questions, please feel free to ask him. I'm just joking. Okay, so there's a two-step process. One is descending, and the second one is about comparison of fibers. So the reduction to characteristic P is actually, for a affine case, is actually a two-step process. One is descending, the other one is comparison of fibers. The descending is basically pushing your all the data you have in a ring of characteristic 0 to a ring of finitely generated algebra over a ring, which in turn is a finitely generated Z algebra. And then when you go to the fibers, you're pushing all the properties through the fiber to a ring of characteristic P. So whatever properties or hypothesis of the theorem you want to prove in characteristic 0, you would like to force everything all the way to its fibers, which happen to be a ring of characteristic P. That's the general idea. These are the two-step process. Okay, so the general idea is if you are given any finitely generated algebra over a field of characteristic 0, the process is to replace the homomorphism from K to R by a homomorphism H sub A from A to A. So RA is R sub A, where it is defined to be R tensor A, where A is a finitely generated Z algebra, and RA is a finitely generated A subalgebra of R, and the map A to RA is induced by restricting the map K to R, and the map H is nothing but the tensor of the map HA with K. So essentially, you're replacing the field K by a finitely generated Z algebra, subalgebra of K. That's the first step. So you want to push all the properties, all the hypotheses you have on the ring R to all the way to RA. And the second step is to study the fibers, R sub little k, where little k is nothing but the A mod M, which is your finitely generated Z subalgebra of K. And the maximum ideal varies over a Zariski-Dent open subset of the so whatever properties you have for R, you want to push it all the way to RK. And the reason is that this guy, R, is a ring of characteristic 0. R sub K is actually a ring of characteristic P. So this is the basic reduction, this is the basic idea of reduction to characteristic P. Okay. So now comes the first step of what the discern data actually mean. Given a ring R, a finitely generated field K, and and M is a finitely generated R module, and N is a finitely generated R submodule of M. First notation, given X is an A algebra or a module, B is an A algebra, then we denote XB to be X tensor with B. So if you have any object which is an A algebra, if the object with the subscript is the ring B, which is finite, is an A algebra, that means that you're actually taking X and tensoring with B. That's what XB actually means. What does it mean for a discern? The discern data for a tuple K, R, M, and N. The discern data is A, RA, MA, and NA. So you're replacing K by a ring A, R by RA, M by MA, and N by NA, satisfying the following condition. So A is a finitely generated Z subalgebra of K. RA is a finitely generated A subalgebra of R, such that the inclusion RA contained in R induces an isomorphism of RK with R. So if you define A and you define RA, you expect RK to be isomorphic with R. So, moreover, RA is A-free. The third condition is that if MA and NA are finitely generated A submodules of M and N, such that NA is contained in MA, and all the modules MA, NA, MA mod NA are all A-free. Moreover, the inclusion MA contained in M induces an isomorphism of MK with M as R module. So you want to make sure that the definition is well defined, like RK being isomorphic to M and MK being isomorphic to M. Okay, so this is what meant by discern data. Now, first, it's existent. How do you actually construct your ring A and RA, MA, and N? So for that, what you do is first you write write a presentation for the ring R. I mean, there's an isomorphism, not inequality. So if R is isomorphic to K adjoint F1 up Xn modulo G1 up to GF, and Xi's are indeterminate over K, and G1 up to GS are basically polynomials. So they are polynomials, mean that they're polynomials over the ring, over the variables F1 up Xn with coefficients K. So these coefficients, so remember that the first step is actually to come up with the finitely generated Z subalgebra of K. So the coefficients of the G may not be integer. So, but you can do the next best thing. What you can do is attach or adjoin all these coefficients of Gi to Z and form a new algebra called A. So A is the Z subalgebra of K generated by the coefficients of Z. So once you do that, you can define G1 up to GS as polynomial over A adjoint F1 up to Xn. So they become on a polynomial because you have attached the coefficient to Z now. So define RA as A adjoint F1 up to Xn modulo G1 up to GS. That's your first step. So this is how you can define your ring A and R. So next is you see the data. First, you define that the finitely generated Z algebra. you have defined what RA actually means, you also have to make sure that RA is actually A-free. So for that, you can use the generic freeness. So this is the general version of the generic freeness that you have. Is A is a Noetherian domain, R is a finitely generated A algebra, S is a finitely generated R algebra, W is a finitely generated S module, M is a finitely generated R submodule of W, and N is a finitely generated A submodule of W. V is W modulo M plus N. Then there exists an A, a non-zero A, such that VA is actually free. This is not very different from the usual generic freeness which you use. The usual generic freeness we have is that R is actually equal to S. M and N are basically zero, so that you have an element in the non-zero element in A, such that VA becomes free. It's the usual generic freeness, but a little more detailed version. One consequence of the generic freeness, which is most useful throughout the nodes, is that if you have MA is contained in NA, and MA mod NA is A flat or free usually, then for every algebra B, we have that the power 1 of MA mod NA comma B is 0, because MA mod NA is flat. And hence, we can actually inject, NB injects into MB. Another way of saying that you can associate MB with the image in MB. So this is one useful technique which will be used throughout all the proof. Most of the first part of the proof in the code. Okay, once you have the generic freeness, then you can localize at a single element of A, such that RA is actually free over it. So you get the second step of the descent data. If RA injects into RK, which is clearly isomorphic to R, thus we may take RA to be a subring of R. So we get the existence of the first and the second step in the descent data. Okay, the third step of the descent data is about descending the module themselves, descending the module and the submodule together. So how do we actually descend the module? So M is a finally generated R module. So you have a nice presentation like this of the form. So presentation matrix is Rij, and the Rij have are members of R. These are the entries of this matrix here. Therefore, R is actually the quotient of the polynomial ring K adjoint F1 up Xn. So you can take Fij to be honest polynomials F1 up Xn and look at its image in R. That will be your Rij. So as usual, what you can do is that the ring A, so we have defined our ring A, we have defined our ring Ra. Now, it could happen that the coefficient of Fij may not be in A. What you do is you can extend your ring A by attaching all the coefficients of Fij into A. And hence, Fij will be members of A join F1 up Xn. Once you have that, you can define MA to be the co-kernel of the image of Fij polynomials. Remember that Fij's are in A join F1 up Xn because we attach all the coefficients of Fij to A. We made your A essentially bigger. And the image of Fij in this situation. And this image and this image are different. This is looking at the image as a quotient of K join F1 of Xn, whereas this image is looking at the quotient of A join F1 plus F1 of Xn. So this is how you can descend your module M to MA. So you can use generic freeness again to localize that a non-zero element of A to make sure that MA is A-free. The next step is to define your module NA and make sure that NA also sits inside MA. If N is contained in M, the M is actually a quotient of free module, so you can think about M as the column vectors and column vector. So let Gij be the matrix with entries in K join F1 of Xn. Consider the image in R such that the image of the columns of this matrix in N will span this submodule. N is a submodule of N. Look at the generating set of N. They will be represented as column. These columns will have entries which are actually images of GIJs. So take the GIJ. As we did before, attach the coefficients of GIJ to A to make A bigger, to make sure that GIJ is also defined in A minus 1. And then the image of the concatenated matrix is the presentation matrix of the quotient M mod NA, that MA is surjected onto M mod NA. Now localize that one element of A to make sure that M mod NA is a A module, and we can let NA to be the kernel of the surjection map from MA to M mod NA, which is nothing but the column of the image of GIJ in N. Localize again by generic freeness at a non-zero element of A, such that NA is A free. I thought we have that M mod N. The descent of M mod N is nothing but descent of M modulo the descent of A N, and all three of them, MA, NA, and M mod NA, are all A free, and they satisfy the third condition of the descent. So this is the first step. So this is how the existence of such a descent, to make sure that you can descend the ring, the module, and its submodule. Suppose you have finitely many modules, you can still do the same thing. You can descend a finite set of modules and its submodule, a finite set of submodules onto it. So if you have a family of finite set of modules, you can define the descent of the finite set of modules which are contained in MA, and they are finitely generated A-free RA submodule of M. That if you look at with respect to K, you get back your MI. So the next question is, if you can descend finite set of modules, what happens to the map between the module? Suppose phi is a map between M and M prime, and we want to descend phi A, which is a map between MA and MA prime. If given M and M prime, we can define what MA and MA primes are. That can be done. The question is, how do we actually define the map phi? What you do for that is, once you have M and M prime, construct M and M double prime. So it's actually the co-kernel of alpha and alpha prime, like we did before. You have a map phi, so you have a map phi 0 and phi 1. So the way we define MA was attaching all the coefficients of the entries of alpha, and defining MA prime will be attaching all the coefficients of entries of alpha prime to A. Similarly, you can play the same trick for phi 0 and phi 1 also. You can attach all the coefficients of the entries of phi 0 and phi 1 too. Once you do that, you can, and the phi 0 and phi 1 are mapped between free modules over RA. So there should be a subscript A here, that's a typo here. So there should be phi 0 sub A and phi 1 sub A. They are free module over RA that we can define. It's induced as a well-defined map phi between MA and MA prime. Okay, and you can localize that one free element to make sure that MA and MA prime are all free, and both MA and MA prime inject into M and M prime respectively. It's something which you can get because of the descent data. So the important part is, even map between modules can be descended down to the A level. Similarly, we can descend short exact sequences of modules too. That is, if you have a short exact sequence, M prime to M double prime, which is exact at M, that means that the kernel of psi is equal to the image of phi, then we know how to descend to MA prime, MA, and MA double prime. That can be done. Now we know how to descend phi and psi to phi and psi A also. And since phi times psi is 0, phi A times psi A will also be 0, because their phi and psi A are basically restriction maps. Now the question is, if the homology at M is 0, is the homology at MA also 0? What you can do here is that look at the homology at MA, and once you tensor with the fraction phi, they become exact because the further tensoring with the K, you get this exact sequence, which is actually exact, sequence which is exact, sorry, and K is contained the fraction field F, so it's faithfully flat, therefore this sequence is also exact. Therefore, now you can show that after localizing at a single non-zero element, HA also becomes zero. There are two ways to do it. You can use general freeness to make sure that HA localized at a non-zero element become zero, become free, and it has a finite rank, but the rank will be equal to the rank here, which is zero. Therefore, HA after localizing at a non-zero element becomes zero. Or you can look at the definition of the first localize at a non-zero element A, and then how do we reach the homology after tensoring with F? It is a directed union of all these localizations. So eventually, at one point, at one state, the homology becomes zero. Therefore, you can localize at that particular element and make sure that HA is zero. So after localizing as a non-zero element of A, the homology at MA is zero. So if your original sequence is exact, then after you descend to the A level, the sequence still remains exact. This is very important because with this, you can actually solve a lot of descent problems. Like if you know a certain intersection works in the original ring, then you can descend it down to the A level, or if your sum is, if there's a certain sum you would like to descend, all these works because the short exact sequence works. And you can make sure that a certain homology is non-zero or zero, that will also work. So preserving short exact sequence is very important. Okay, so certain kind of uniqueness. So given two sets of choices indexed by A and B, you can actually define a sufficiently large finitely generated Z algebra C that it contains both A and B, in which the distance are basically the same thing. What I mean by that is, first one remark, you know that R is isomorphic to RK. It is nothing but a direct limit of RB, where B runs over all the all the A algebra, which sits inside K and contains A. So if A is contained in B, then RB is isomorphic to RA adjoint B, and it is contained inside R. So if A and B are not related, construct their respective descent, RA contained in R and RB prime contained in R, such that the RK is R and RK prime is also R. And fix a finite set of generators theta I for RA and theta J prime for RB prime over A and B respectively. Then by the freeness condition, if for any C which contains A union B, RC is C adjoint theta I and RC prime will be C adjoint theta J prime. But if your C is sufficiently large, which contains both A and B, then theta J prime is in RC, and you have that RC C adjoint theta I and theta J prime. Similarly, the same logic will also tell you that theta I will be inside RC prime, therefore they're basically the same algebra. So essentially, given two choices of descent, you can enlarge the ring and make sure that the descent will be the same algebra. Suppose you have two choices of descent for a module, that is two RA modules, W and W prime, which are A free, and such that when you tensor with K, you get the module M. As before, the same idea, choose the finite set of generators Wi and Wj prime for W and W prime over RA. And for any finitely generated Z algebra B with A contained in B, contained in K, B tensor W and B tensor W prime may be identified with the RB submodule M generated by W I and Wj prime. One tensor W and one tensor Wj prime. So for sufficiently large B, Wi sits inside B tensor W prime, and Wj prime sits inside B tensor W. So if your ring B big enough, both the modules are basically same thing. So both the descent become the same. So the idea is actually to keep increasing your ring A so that your descent is the same. And make sure that all the properties you have in the ring R can be descended down all the way to A. Okay, so further properties which you can achieve via descent. So if M is a non-zero module, then MA will also, the descent MA will also be a non-zero module. And MA is A-free module. We get by generic freeness. It's having the rank at the same dimension of M, which is usually infinite. So if the map phi is not injective, that means it has a non-zero kernel, then you can make sure that the descent also has a non-zero kernel using the same idea here. So if your co-kernel is non-zero, you can make sure that the co-kernel of the descent is also non-zero. So the kernel, image, co-kernel are all A-free, and the map being not injective or not surjective can be preserved. The second step is if you have a finite chain of modules, like Mi sitting inside Mi plus 1, Mi plus 2, then we can arrange A to preserve the inclusion, that is MIA contained Mi plus 1A is contained in Mi plus 2. It's basically coming from the short exact sequence. If N is N prime plus N double prime, then we can arrange A so that NA is NA prime plus NA double prime. The sums can also be preserved. If you have the intersection, then we can arrange A so that the intersection was also preserved in MA. Homology of a finite complex of modules can also be preserved via descent. A finite set of complexes, finite complex of modules, and you have the homologies appearing. Some of them may be zero, some of them may be not zero. All these can be preserved via descent. Split exact sequences can also be preserved via descent. If you have an ideal I in RA, then the A algebra, RA mod IA, is said to solve the descent problem for the K algebra R mod I. And thus, if RA mod IA is contained in R mod I, and if I is radical, prime or primary in R, and so is IA in R. So, okay. And if F1 like such form a regular sequence in R, so does it form in the descent R. For example, more generally, if you have a M regular sequence, then you can make sure that they form an MA regular sequence after descent. What you can do is you can descend all these finitely many modules, M modulo F1M, M modulo F1, F2M, descend all of them to the A level and make sure that Xi plus 1A is actually a non-zero divisor in this module. So, but that is reduced to just checking if you can do it for one element. If you know that one element X is a non-zero divisor in M, then you just have to check that one element XA, the descent of X to A, is a non-zero divisor in MA. But that part is clear because MA actually sits inside M. You can also achieve this by making sure that you preserve all the homologies of all the fluid complexes on the sequences X1 up to Xi. So the next is if you have J is a ideal of nilpotence in R, and J intersects in RA. RA will contain all the nilpotence in R. If A is large enough, you can make sure that J contains all the generators of J itself. So if you look at one element, you can make sure that RA, J, RA mod J are all A-free, and the RA mod J is the descent of R vacuum. And if P1 up to Pn are minimal primes of R, then so is P1A, P2A, blah, 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 Pna. Descent of the prime sequence, P1 up to P. You can individually descend R mod Pi to RA mod Pia, and you can also preserve if J the intersection of Pi, then J A becomes the intersection of Pi, finitely many primes, of course. So these are all the properties which you can actually descend down to to the A level. So essentially, you're replacing your original ring of characteristic P with the ring RA, where A is a finitely generated Z subalgebra of K, and you're making sure that you can descend regular sequences, sums, intersection, prime, minimal primes, everything down to the A level. So still in characteristic 0, but this is the first step. Okay, now come the second step. The second step is going to the fiber level. So first, a couple of definitions. So R is said to be an absolute domain. Is geometrically reduced if the tensor of R with the algebraic closure of K is a domain already. And the P is called an absolute prime of R if R mod P is an absolute domain. And K algebra R is called geometrically reduced, geometrically normal or geometrically connected if the tensor of R with the algebraic closure of K is regular, normal, or respectively connected. Okay, so fibers. So if you have so now we have descended to the A level now. So if you have a map from A to RA, the RA is a finitely generated A algebra. And P is a prime idol of A. We call little k to Rk as the fiber of A to Ra over P, where K is AP mod P. It's true for any prime of A. So if A is a domain with a fraction field F, then F to RF is called as the generic fiber of A to Ra. The generic fiber is kind of very important because the generic fiber is contained inside the capital K, and therefore it's faithfully flat. For any properties you have for R, you can get it to the generic fiber. Okay, so if the P is a maximal ideal, the corresponding fiber is called as a closed fiber. And this is a very important definition. Suppose you have an A as a domain, then a property holds for all fibers over prime not containing a certain element A, then the property holds for almost all fibers. So another way of saying that, if you look at all the primes which runs inside a Zariski dense open subset of R, and property true for those fibers, then you say that it is true for almost all fibers. So the idea is that whatever property you have for the ring R, you want to make sure that it is true for almost all fibers. Okay, so what is the advantage of going to the fiber level? Suppose MA is a maximal prime idol of A, then there exists a prime number in MA because A is a Z algebra basically. So if you take a maximal idol of A, to contain a maximal idol of Z, which are basically prime numbers. So you have a prime number inside MA. If you look at the fiber K to RA for MA, then it will be AMA modulo MA mod MA. RK will be of a characteristic P. So if a property holds for R, then it is desirable to descend the property all the way to the fiber RK. So this is the main idea behind descending to characteristic P. So what properties you have in R can you actually push to the fiber RK? And remember this definition again. So some of the properties we discussed here will be true for almost all fibers. Not all fibers, but almost all fibers. Okay, so the next part of the talk requires that some of the statements will be true for almost all algebras over M. So the theorems will be basically giving a hypothesis on the generic fiber, and one will be asking if it is true for almost all fibers. The conclusions of many of these theorems actually not just true for fibers, it's actually true for any algebra B over A, any A algebra B, such that A has a invertible imaging. So if it is true for almost all B, then it will definitely be true for almost all fibers. So in setting of the next theorem, you have A and RA, and FA is a fraction field of A, and K is an extension of F, and MA is a finitely generated RA module, SA is a finitely generated algebra over A, and WA is a finitely generated SA module. So if you have a map between R and S, you would like to study the map between RA and SA and its corresponding modules and so on. Okay, so given an A algebra homomorphism from RA to SA, and an RA linear map from MA to WA with the kernel NA and the co-kernel CA, then for almost all B, MB to WB has the kernel NB and CB. So if you know that M to W is injective, then for almost all B, the map MB to WB will also be injected. In particular, for almost all fibers, MK to WK will also be injected. Similarly, if you know that M to S is surjective, then for almost all B, the map MB to WB is surjective, and for almost all fibers, MK to WK is surjective. The basic idea behind the proof is you have a sequence of the kernel NA and the co-kernel CA localized at a non-zero element to make sure that all the modules NA, MA, WA, and CA are all A-free. And then use the main observation given in the during the generic training, and you can see that the being injected or surjected can be preserved for almost all fibers. Okay, so next is for almost all B, dimension of RB is the dimension of B plus the dimension of R. And in particular, for almost all fibers, dimension of RK is the dimension of R itself. So if your original ring have a certain dimension, then you can preserve it when you go to almost all fibers. And if MA is the finite complex or finitely generated RA module with the homology HA, and for almost all B, the homology of MB is HB. And so for almost all fibers, the homology of MK will be HW. And for every value of I, for almost all B, the tor I of MB, WB is the tensor of the tor I of MA, WA with B. And the ecti of MB, WB is the tensor of ecti of MA, WA with B. So the tor modules and X module can also be pushed through to the for almost all fibers. Suppose you have N prime, N double prime submodule, such that N intersection with N prime is N double prime. Then for almost all B, NB intersect with NB prime is NB double prime. So for almost all fibers, NK intersect with NK prime will be NK double prime. Okay. So if the annihilator of MA is equal to IA, or the annihilator of IA is NA, then the annihilator of MP is IP, or the annihilator of IB is NB for all B. So in particular, all these statements are true for almost all fibers. And if NA colon NA prime is IA, then NB colon NB prime is IB for almost all B, in particular true for all. And K colon NK prime is IK for almost all fibers. And if you have a sequence H1 of Xn forms a regular sequence over M, then for almost all B, its image in RB forms a regular sequence in MB. In particular, the sequence forms a regular, the image of the sequence in the fiber also forms a regular sequence in MK, with the fiber of M. If IA is the ideal of RA, then for almost all B, the depth is also preserved. So the depth of MB of IB is the same as depth of MO prime. So for almost all fibers. So the depth, dimension, regular sequence, colon, intersection, annihilators, everything can be preserved for almost all fibers. So once you have this type of notion, questioner, if R is geometrically regular, then the fiber RK will also be geometrically regular for almost all fibers. And can be checked by using the Jacobian criterion for regularity. And if F to R, if R is geometrically reduced, then so is the fiber RK for almost all fibers. And if the R is an absolute domain, then so is the fiber RK for almost all fibers. So all the good properties you have of the ring R can be all the way to the fiber for almost all fibers. Okay, yeah. So now if you have the ideals of R and M finally generated RA module, and if XA is an element of RA, so that X is not in any minimal prime of R, then for almost all B, XB is not in any minimal prime of R either. So this can be achieved primarily because if you localize an element at a non-zero element of A, you can make sure that there's a one-to-one correspondence between the minimal prime of RA and RF or R. So there's a bijective correspondence. So and then you can make sure that if X is not in the minimal prime of R, then for almost all fibers it cannot be in the minimal prime of R. So if you can do it for one element, you can do it for a finite sequence also. In fact, one of like such is a sequence of elements of RA that Xi plus 1 is not in any minimal prime of X1 up Xi for almost all B. Then Xi plus 1B is not in any minimal prime of X1 up Xi either. For almost all B, the height of IB is the same as the height of I, and the dimension of RB mod IB is equal to the dimension of B plus the dimension of R mod I. In particular, for almost all fibers, the height is preserved when you go from the ring to the fiber, so is the dimension of the ideal. So dimension of the RK mod IK is the same as the dimension of R mod I. So if PA is a prime ideal of RA of positive height, that the height of P is H and the dimension of P is D, then for almost all fibers, PK is not a prime ideal, but you get the best thing. You get that all the associated primes are minimal primes Q, the same height H, and for each of them, the dimension of RK mod Q is D. So the height and the dimension, these invariants can be preserved. And after localizing at a non-zero divisor at A, the elements of MA correspond bijectively to the associated prime of MN. That part is clear because a generic freeness, you can make sure that the associated prime of MA correspond bijectively with the associated prime of M. So for almost all B, the associated prime of MB is the union over the associated prime of MA of the associated prime of RB mod P. Okay. One small part, this is, you can get it just by, this part you can get directly by expansion and contraction. You don't need generic freeness. Just localize at a non-zero element and you should be able to get it. Now, for almost all fibers, the set of minimal primes of MK is nothing but the union over the minimal primes of MA of the fibers associated prime of RK mod PK. And if MK or RK has no embedded prime, then the same is true for MK, the fiber MK or RK for almost all fibers. And if I is unmixed, then for almost all fibers, the fiber of I is also remaining unmixed. So all the properties you have here can be, for the ring R, can be pushed all the way to the fiber for all fibers. Okay, so let A to RA suppose the X1 of like such, and there be regular sequence, be a system of parameters in R. Then for almost all fibers, the images in RK are also forming a system of parameters. And therefore, the natural question is if the ring R is Quine-Macaulay, then tau is the fiber RK for almost all fibers. And if R is Gorenstein, then tau is the fiber RK for almost all fibers. And so the property of being Gorenstein or Quine-Macaulay can be pushed all the way to the fibers also. Okay, so if you have ideal I of Ra, J is the union of all the nilpotents of R. Remember that JA is nothing but the descent of J. Then for almost all fibers, JK is the ideal of all nilpotent elements of the fiber RK. And if Ra is reduced, then the fiber RK is also reduced for almost all fibers. And if QA is a ideal of RA, so that Q is a radical ideal of R, then the fiber QK is a radical of IK for almost all fibers. And if I is radical, then the fiber of I is also radical for almost all fibers. So you can descend a lot of properties to the fiber. So if you have Quine-Macaulayness and the rigidness condition appearing, then it's natural to expect what happens to the normality condition. So if R is normal, then for almost all fibers, the fiber RK is also normal. And if R is reduced and S is the normalization, then for almost all fibers, the fiber RK is the normalization. Furthermore, more interestingly, if J is the integral closure of I, then the fiber JK is the integral closure of IK for almost all fibers. So you can descend pretty much all the important conditions from R to the fiber RK. So you're going from a ring of characteristic 0 to a ring of characteristic. Okay. So this goes for the reduction to characteristic. So one small thing, a couple of minutes more. So I have a couple of minutes more. But this is something we're going to be using in the next talk. So I just want to quickly define what type closure in characteristic 0 also means. So if R is a finitely generated algebra over field K of characteristic 0, if N is contained in M, a finitely generated R module, we say that U is in the K-type closure of N if there exists a descent A, R, A, M, N, N, A of K, R, M, and N, such that UA is in NA star in MA over A. So it's a lot of symbols. So this is NA is the descent of N, and NA star in A, the type closure over A in MA. That's what this definition means. So we say that once you descend it over, so UA is in the type closure of NA if for almost all fibers. UK is in the type closure of the submodule generated by NK in MK. So this is a ring of characteristic 0. You pushed it all the way to the fiber, which is of characteristic P. So you have your definition, usual definition for characteristic P here. But one thing to notice here is that if you want to check that UK is in NK star, you use the test element CK. But once you keep changing your maximal idea, the test element you use also keeps changing. But Hoxha and Hunike proved a really important theorem. In fact, a pretty deep theorem which says that the existing element 1CA is in RA, such that if NA is contained in NA, if you want to test if UA is in NA star, you can look at CK UK power Q is in the Frobenius power of NK MK for all Q for all big enough. So one advantage is you have one CA which actually works when you go to almost all fibers. You don't really have to keep changing your test element. This is not easy, and it goes through the theory of something called as a universal test element, but I'm going to really jump over the whole section. But you're welcome to read that in the note. And they give a very good introduction and a theorem of how to build this universal test element. Okay, so once you have this, the next question becomes your choice of distance. So say that if there exists a distance that you can then go over to the fibers and check tight closure. So they go and show that it doesn't really matter which distance you take. So if you have two choices of distance, then if you want to test that using end closure, you just test their it being the tight closure with respect to either of their distance. So U is in N star if and only if UA is in NA star or NB star. Same thing. Okay, so a couple of properties and then should be done. But with many of these properties which you see for characteristic PK, tight closure and characteristic P case is also true for the characteristic zero case. So if you have modules N prime and N in M, are finitely generated R module, U is in M and V is the image of U in M mod N, I is an ideal of R, then U is in N star if and only if V is in U star, 0 star in M mod N. And N star is a submodule of M containing N, R submodule of course. And if N is contained in N prime contained in M, then the tight closure of N is contained in the tight closure of N prime. So since you have N is contained both N prime and M, you can take the tight closure with respect to N prime or the tight closure with respect to M. As you expect, the tight closure with respect to N prime is contained inside the tight closure with respect to M. And if you take tight closure twice, you get tight closure 1. And the intersection of the tight closure is contained inside the tight closure of the tight closure of the intersection is contained inside the intersection of the tight closure. And the tight closure of the sum is the tight closure of the sum of the individual tight closure. And IN, the tight closure is an N, where I is an R ideal and N is an R submodule of M, is got by taking the tight closure of I in R times the tight closure of N in M, times take the tight closure of the product in N again. And the tight closure of N colon I is contained inside the tight closure of N colon I, and if N is equal to N prime, then N colon I star is the same as N colon I. And suppose you have Ni is a submodule of Mi, which is a finitely generated R module. We can identify N with the direct sum of Ni, with the image of M, which is the direct sum of Mi. Then the injection of the direct sum of closure maps the direct sum of tight closures with the tight closure of N. And if L is the field containing L and S is a finitely generated L algebra, R to S is a K algebra homomorphism. If U is in N star, then 1 tensor U is in the tight closure of the module generated by S tensor and in S tensor. This is the persistence of tight closure. And if J is a nil radical of R, then J is contained in the tight closure of 0, and so J is contained in I star. This for ideal we already know this. Consequently, Jm is contained inside N star. And if you have R is a direct product of Ri's, and M is a direct product of Mi's, with N being a direct sum of Ni's, and with N is a submodule of M, then if you take a tuple, U1 up to UN is in the tight closure, if and only if the UI is in the tight closure of the individual component Ni over Mi. So this is Mi slash Mi. So if you want to test the tuples in the tight closures, if and only if the individual entries are in the tight closure of the corresponding component. And thank you very much. I will stop here.
Thank you, Vivek. We will take questions. You can open your mic and ask questions if you have any. Maybe I can ask a few questions before people think about their questions.
Okay.
Yeah. So through this process, uh, we have a notion of type closure in characteristic zero.
Right.
And so do we have numerical criteria like the Hilbert-Kunz multiplicity detects elements in the tight closure?
Oh, that's a good question.
Do we have such a theorem in characteristic zero for tight closure of ideals?
I mean, safe to say I don't know. I, I, I don't really know that if you can descend down the Hilbert-Kunz multiplicity. The only issue I'm finding is that you cannot descend an infinite sequence. For example, if you want to compute length, you really have to descend sequences down. I'm not sure. Better to say I don't know if you can do Hilbert-Kunz multiplicity.
So can I ask Craig whether he knows about existence of such a criterion?
Hey, I don't off the top of my head. I think Trivedi is here. She probably knows better than anybody about Hilbert-Kunz. One question I had for Vivek was, were you going to talk at all about using approximation to descend from arbitrary equicharacteristic rings?
Sorry?
Yeah.
Hello? Yeah. You asked a question, Professor?
I was just wondering if you were going to talk about art and approximation at all.
No. I mean, I might probably give a no, none of the approximation part at all.
Yeah.
I might do it at the very end a little bit, but I don't. That requires a lot more time.
And do we have the notion of F regularity in characteristic zero?
Sorry?
I mean, characteristic P, we define F regular rings and weakly F regular rings.
Right.
So are they studied in characteristic zero? Do we have large classes of rings which are F regular?
I don't know. Probably the same definition for almost all fibers. Check that it's weakly F regular.
Right.
And that, yeah, the trouble with that type of definition is that in the descent data, you only do finitely many things, basically. So anytime you have a quantification over all ideals or over all, over an infinite number of things, the descent will break that. So there may not, the notions aren't as robust because of that.
But some class of singularity positive characteristics, do they give rise to new singularities in characteristic zero?
Not that I know of. I mean, log terminal is the same as what reduces to F regular, basically. So,
Okay. Yeah.
and the Hilbert-Kunz, I think you should ask Trivedi about.
Craig, hello?
Right.
Yeah.
Yeah, actually, I would. Yeah, I had a question. Maybe Craig can answer. Suppose you take a ring over containing a field of characteristic zero. So when you're looking at the tight closure of an ideal in characteristic zero, does it mean that if I go reduction mod p for infinitely many primes, it belongs to the reduction mod p of that ideal? Oh, I didn't quite understand. Yeah.
The tight closure, yes.
Yeah. Almost all. Yeah.
No, it's for almost all p or infinitely many p's.
Almost all.
Yeah. I think my memory is we defined it for almost all.
Ah, okay. Yeah, okay. Yeah, thank you.
There's some strange things that happen there that make it, like often when you do that definition, it turns out that even for large P, it's in the Frobenius closure or something like that, when it's in the tight closure in characteristic zero. So there's a lot we didn't understand there. I think that's my memory. It was a long time ago when we did this.
Okay, thank you.
Yeah. I have to go myself now. I'm sorry for class.
Okay. Okay.
Thank you
Thanks.
for your talk.
Yeah. Thank you. Yeah. So, are there any other questions? So there is a question from Kriti. Kriti, can you ask your question? The question has disappeared. Can you ask your question?
Yes, sir. Hello. There was a discussion about relating the singularities in characteristic P when we
Right.
are doing a reduction to characteristic P. But
Right.
we already know there are some singularities like rational singularity and pseudo-rationality.
Right.
So is there a connection with that, like closeness of these ideals? Or do they characterize such kind of things?
I think that what Craig was trying to say. It may not make sense through this reduction to characteristic.
Okay.
Okay, so it's like if you do have the notion of rational singularities in characteristic zero, but once you have if you want to do it through the reduction to characteristic P, I don't know how that's going to behave. I mean, I'm pretty sure it shouldn't be related.
Oh, okay. Okay. Thanks.
Any other question? Okay, so if I don't see any questions. So Vivek, thank you very much for your talk, and we will meet on Friday.
Okay, sure.
Yeah, thank you.